So, yes, as Fan said, I'm going to talk about this rather complicated subject. This arises from the last meeting. Now, there's the online VSA-Oberlin discussion, and in the chat after that, there was a lot of conversation about transients, and I thought it got rather muddled and people talking at cross purposes, because this word has many different senses and people weren't all talking about the same thing. So my task for today, afternoon as far as I'm concerned, is to try to give an overview of the different things that transients might mean, to give you a bit of perspective. I'm going to cover a lot of ground. I hope it's not too confusing. So, first of all, do transients matter? Now, some of you will have heard this demonstration before, but if you haven't, you just have to hear this. So listen to something and ask yourself, what instrument are you hearing? Hear somebody nod. Did you hear a sound there? Is the audio working? Yeah, that's good.
Can you play it again, Jim?
By going to the slide again. But now what I've done there is I've cheated. That audio file was played backwards. I play it to you in the other direction. And I think you know what that is. Now, there is a persistent bit of fake news, I guess is what we call it these days, that musical timbre is all to do with frequency content, balance of harmonics and all of that. Well, those two sounds had completely identical frequency content. It was the same waveform, simply played forwards and backwards. The only thing that was different was the time dependence, but I hope you would agree that you perceived them really rather differently, as you instantly recognized the piano when it was played the normal way around. The funny sound of a backwards piano, you simply wouldn't have known what it was unless you've heard this before and you say it's a backwards piano. Right, so transients potentially are important. All right, what do we mean by transients? Now, this is where the muddle potentially comes in. There are many different senses. First of all, there's a broader and a narrower sense of the idea of transients. In the end, all the word means is it's the opposite of steady. So anything that's varying in time rather than being steady is in some sense transient. Well, from that point of view, all violin playing consists entirely of transients. Here's a few seconds of violin playing. You should now hear it. We'll come back to this many, many times. Now,
I'm sorry, Jim, are you sure you are sharing your sound? Because I feel like the quality is not that good. I'm wondering whether we don't hear it through your loudspeakers.
Well, yeah, no, we had this. I'll have to, let me just try again. I was expecting it to ask me when I share.
When you see it in the lower left-hand corner box that you check.
Yes, indeed.
Yeah, I probably did something. Oh yeah, my fault. Absolutely right. Absolutely right. Okay, let me play that again. So we play that slide. A little bit of regular violin playing. It may sound a little odd. I will explain why in a moment. So the broad sense of transient is that everything, there's no steady sound anywhere in this. Everything is varying in time. The narrower sense that people often use is the idea of starting transient, that's specifically about the start of notes. And that's what I've pulled out. The four little red stripes are highlighting note transitions, and they're the things that are pulled out on the right-hand side of the screen in a zoom view of some note transitions, some ending and starting transients. Now, in order to understand what these waveforms are, you need to know something. A lot of you will know this already, but you have to see this anyway. You need to know roughly what happens when you bow a string. So this is Helmholtz. He was the first one who discovered this back in the 1870s. And this is the ideal version, but I hope this video is playing all right for you. Over here, you've got, here's your bow moving upwards. And the string has this really peculiar triangle shape with this corner that shuttles around. And if you watch closely where the red line crosses the bow, all the time the corner is traveling around this long way to your finger and back. The string is moving with the bow, the string is sticking to the bow hairs. Helmholtz's corner arrives, it flicks it off, and while the corner travels the short way to the bridge and back, the string is sliding. So it's a stick-slip oscillation, but its timing is governed by this magic corner that circulates. Now, if you want to see what's going on in the bowed string, the waveform to record is the thing you're seeing in blue at the bottom. This is the waveform of force that the string is exerting on the bridge. And that's the input force that's driving the body. And ideal Helmholtz motion generates this sawtooth waveform of force. It's the sawtooth is this way up because we're bowing. If we change bow, so the bow is moving downwards, the sawtooth would face the other way. Now we go back to this picture, and that snatch of violin sound you heard was recorded through one of these force transducers on the violin bridge. And you look at these waveforms, and towards the right-hand side of all of them, you can see this sawtooth wave. This is real data, but it really does do this. All of these notes end up doing a version of Helmholtz's sawtooth. Exactly how they get there is something we will talk about at enormous length in the next 3/4 of an hour or so. Okay, but now, as I said at the beginning, there are many senses of the word transient. And this is where I think people were to some extent talking at cross purposes last time. Now let's have a violin in my hand. The first rule of science is always do the easy things first. So some transient things are what we call linear. It's a technical term meaning easy, as opposed to non-linear, which is a technical term meaning difficult. There are two types of transient behavior that I can produce on this violin, which are simply linear. One is the noise you hear when you tap the bridge, and the other one is the noise you would hear if you pluck a string. Are you hearing these coming through well enough? Yeah. So the body tap and the ringing names the strings, but then there are the things that the player does with their bow. And they're in blue because they're non-linear, and we'll come to those. I'll talk a bit about all of these things, and they're not unconnected with each other. So start with the easy things. So anyone who's done these sort of violin measurements in Joseph's rig or whatever, with one of these little miniature hammers, you're rather used to hearing this tap noise on the bridge, because that's when you hit the bridge with your hammer. You record the response in one of two ways. If what you want to know is how the body is vibrating, then you record on the bridge and measure something we call the bridge admittance. I'll show an example in a second. If you want to know something about the sound of the violin, you record with a microphone or lots of microphones at some distance. Either of those will do. If you do the bridge admittance thing, then you get this kind of curve. A lot of people will have seen this sort of thing before. This is a frequency response function of a lot of violins. I forget how many there are here. There are some pretty famous old names in here, and there are some fairly famous contemporary names in here. The thing that I see when I look at this, just as a sort of vibrations person, and if this was any other kind of vibration measurement problem, I'd say they're all the same. All violins are essentially identical. Now, that's a frivolous remark, but it's not. It's a serious remark. It tells you something. everything looks remarkably the same, and yet you know that some violins are a little more valuable than others. A lot of the information about the quality of a violin is captured in these curves, and yet all violins look very similar. And that is a view of something that people kind of know, which is that there's something subtle about musical instruments. Musicians care about small details. Otherwise, they would think all violins were identical, because violins actually only differ from each other in rather small details. And you always have to work rather hard to get that information out. Here's a version of that clonk noise. I shall keep on talking about these clonk noises. And that's it, that's a particular violin, it doesn't really matter. And we'll come back to that in a moment. That tells us something. Before I come back to those, so let me talk about the other thing, which is a linear effect. I don't know if Colin Goff is in the audience, but I suspect he probably is. This is for him, really. Colin, as everyone knows who's involved in Oberlin, is always very keen on the ringiness of the strings, as saying something about quality of instruments. Well, I'm just going to say a little bit about ringiness of strings for Colin's benefit. So does it make any sense to say that the ringiness might be an indicator of instrument quality? Colin likes it, that's clear, and that's fine. If Colin is happier with an instrument, then he plays better and it sounds better. I want to say 2 or 3 things about this. Nicely balanced between positive and negative things. First of all, it's an easier problem. Thinking about that sort of noise takes us into the world of plucked stringed instruments. We know a lot more about plucked stringed instruments. They're easier, not infinitely easy, but easier than bowed instruments. So we can say something about it. And there's one really simple thing we can say. If by ringiness you mean how long the string rings on, so the damping of the plucked string vibration, then first of all, it's only the open strings that matter. As soon as you finger stop a string, you contribute so much extra damping with your finger, you get that characteristic pizzicato sound. The ringiness is dominated by your fingertip, how fleshy it is, how hard you press, all of those things. Ringiness, if it's being a good thing, you'll be talking about the open strings. And there's another really simple thing you can say, which is that any note, if an open string on a particular instrument is particularly ringy, I think that will guarantee that if you bow that note, it will be quiet. Because ringiness means that the string is keeping its energy for a long time. If the string is losing its energy efficiently to the bridge of the instrument and into sound, the sound must be dying away faster. A loud note means it gives its energy away to the body more efficiently. So a ringy string probably means that when you bow that open string note, it's not very loud. Quiet instruments as a quality measure, not really good. But I noticed a funny thing while doing this. So if we say, okay, which of these strings is most likely to give me a ringiness impression? And the answer is it's going to be the E string, because the E string has the least internal damping. All the other strings, Fan will know this, have got complicated overwrapped construction with windings and core material and friction and stuff going on. So they have higher damping. The E string, it's either just a plain piece of steel wire or maybe it has a little bit of wrapping. The E string is intrinsically ringier. Well, look back at that plot of all those violin admittances and see where the open E string lies. Here's the fundamental 660 Hertz. Here's the octave of that. The fundamental of the open E string lies in this deep trough that all violins more or less share. Not only that, but the octave of it is not far away from this other dip that most violins share. So actually, I don't know if this is a coincidence, but the open E string of a violin in conventional tuning is ideally placed to be rather ringy. And then, of course, the instruments are not completely identical, so there will be some variation from instrument to instrument in just how ringy that is. So maybe there's something in there. But I thought it was a curious coincidence. I wonder whether that matters. Anyway, now we turn to the more difficult stuff about what happens when you bow a string. And we get these pictures. We're going to keep on seeing this set of 4 note transitions. So I need to introduce you a bit to how a bowed string works. We've seen Helmholtz's motion already. So I need to orient you a bit with how to look at things like this. So we need to know what can go wrong when you bow a note. Everyone knows that you can do all kinds of horrible things with a bow on a string in a way that you can't do with a plucked string. It always sounds all right. Are these good notes or not? How did the player create them? And how do these different transients affect the sound? Those are things we want to explore. So we're going to start by thinking about steady bowing. This is not about transients, but it orients us. This is a diagram that probably lots of you have seen before. This is something called Schelling's diagram, and this captures something about the experience of playing any bowed instrument, which all players know, although they may not have thought about it like this, that if you fix the speed of bowing, just so that we can draw the picture, then the player has 2 variables. They can choose the force, what players sometimes call bow pressure, because they don't understand about physics, so I will call it bow force. And you can choose the position on the string where you place your bow. And for a given, now we're then plotting, this is bow position on the string, bridge at this side, fingerboard at this side. This is the bow force, low at the bottom, high at the top. And in that diagram, there's this kind of schematically, there's this wedge-shaped region where you can get Helmholtz's motion. If you press too hard, you go above a limit, the maximum bow force. If you don't press hard enough, you go underneath something called the minimum bow force. To see what those mean, we need to see some data. So here are some typical measured waveforms of this bridge force going with those regions. So the Helmholtz region produces this sawtooth wave that we've seen already. What happens if you don't press hard enough, you slip below this minimum force line, is that you might get something like this. And you can see it's a kind of double sawtooth, or it could have been a triple one. The string slips more than once over the bow hairs every cycle. It results in your violin teacher telling you off. They say you didn't get into the string properly. Horrible surface sound. If you press too hard, then you get some kind of horrible raucous crunch, and you don't even need your violin teacher to tell you off for that one. You know you've done that wrong. And the motion ceases to be regular. They won't always look like this, of course. This is just a typical example of an irregular motion. But the 3, just fix these 3 ideas in mind. You've got the Helmholtz sawtooth. You might have a sawtooth with little extra saw teeth added to it, or you might have something rather irregular and noisy. Now, those 3 types of things are going to play a role when we come to look at transients. Now, the person, I hope Anders Askenfeldt is in the audience somewhere. He was hoping to be here. The person who thought most deeply about what happens when you bow a string, and particularly about the transients, was Knut Göttler, and we miss him greatly. Here is Knut, along with a number of other worthies of the musical acoustics world, in my back garden a few years ago. Knut, for people who didn't meet him, he was a double bass player with star quality. He was a famous player and also a famous teacher of the double bass. His double bass method is still widely known in that world. And relatively late in life, he got interested in science, and he started using these computer models that I'll talk about in a bit to try to say something that he could use in his teaching, telling his pupils how to play the double bass better. Now, the double bass has the violin problem, only it has it in spades. The notes are so low that you don't need to have many cycles of the initial motion looking wrong, and the note is over before you've even got the Helmholtz motion going. So bass players are particularly keen on getting super clean starting transients. And that's one of the things Knut thought about. We'll come to that in a bit. Knut did lots of other things. I will talk about two of them. And the one I want to start with is this. You needn't read all this small print here. This is just a paper that Knut wrote with Anders Askenfeldt as part of Knut's PhD project, I guess. And what they did was that they did an experiment to find out how good does a transient have to be before musicians will accept it. And then if you look at what musicians actually do they stick with the rules? So they did two tests. They did a listening test and they did a player test. Now, Knut and Anders classified starting transients into three types. And by a wonderful coincidence, I've got examples of all three of them here. This first one doesn't count. This one, if you look at the sawtooth, it's still going the same way at the end as it was at the beginning. So this is not a bow change. This is a finger change and a little accent with the bow, but it's not a real start. All the others involve a bow change and the string starting from cold and the player somehow wanting to get Helmholtz motion going. And there are three things that might happen. You might get it spot on. This is a perfect transient. This gets into the sawtooth regular pattern straight away, right from the first cycle. There are two things that might happen, and they are the two other things we saw in Schelling's diagram. We might get a bit at the beginning, which looks a bit like the raucous stuff. We might get some irregular, scratchy stuff. Or you might get a beginning that's got this double sawtooth. Can you see that in here? And then the second one dies away and you get the ordinary sawtooth after a bit. So you might have a start that has a bit of double slipping, or you might have a start that has a bit of raucous, scratchy stuff. Knut and Anders describe those as this one sounds choked or creaky, this one sounds loose or slipping. This is string player speak here. And they generated lots of these transients with a bowing machine, and then they got lots of people to listen with headphones and vote for whether this was a good clean transient or not. And they put some numbers on this. They found that for this kind of transient with a scratchy bit at the beginning, it's got to be the transient bit before the sawtooth starts has got to be less than 50 milliseconds long. The ones double slipping, loose slipping ones could be a little bit longer. They could be up to 90 milliseconds. Now, being acceptable doesn't mean they all sound identical. The four things we've got here will all sound a little different, but all of these transitions happen within the permitted time, and all of these would pass muster with your violin teacher. So that's a number. Then they did an experiment with actual players. They got them to play, lots of players to play three different pieces, standardized pieces. Then they gathered the string motion, they laboriously looked at all the transients and counted stuff up. And these are simply histograms of the length of the pre-Helmholtz transient. So 0 in the middle. And what you can see for three different pieces, three different bowing styles. The biggest peak always is on 0. The most common single transient was the perfect one. Players quite often got it right. It's got the multiple flyback. These are the loose slipping, double slipping ones on this side with this acceptance limit out at 90 milliseconds. These are the scratchy ones on this side, acceptance up to 50 milliseconds. And you can see that with very few exceptions, almost all the transients that these players did, and they weren't told what the experiment was, they were just told to play these pieces from the core repertoire. And almost without fail, they are within these limits. They hardly ever get something wrong, and quite often they get it spot on. But of course, that doesn't come easily. That's what all those hours of practice are about. Learning that nearly all the time, or nearly every note, or nearly every instrument, you get a crisp start, if that's what you want. If you want a funny start with some funny bowing, that's a different story. But if you're just playing something cleanly, good players can do it. Right, now, what's going on in these different transients? So I've talked a little bit about aspects of transients that matter to players, which is where Knut was coming from. I'm guessing that this audience is more heavy on makers than players. Two questions that an instrument maker might be interested in is, how does the body of the instrument affect the sound of a transient, a played transient? And how does the body behavior affect the player's sense of how easy is it to play those transients? So we'll say something about those two. And again, I've arranged them in order. We'll do the easy one first and the more difficult one later. Now, how does the body affect the sound of a transient? Well, curiously, for those who don't already know this, two things I've already shown you give you kind of the whole answer. I'll say what I mean by kind of in a moment. But the claim is that if you measure this force, remember, this is the force that the string is exerting on the bridge. So that's the input force that's driving the body. And if you know this clonk noise, if you know what happens when you apply a force to the bridge, either what happens to the body or what do you hear in your microphone at your chosen listening position, and you can put those two things together and make a sound that should be the sound of that violin at that microphone. I'll play you two examples. Claudia will say, oh no, not those again. These come from her project. This is Claudia's project in Cambridge years and years ago, which is what got her seduced away from the nasty world of wind instruments into looking at violins, and she's never looked back. So play your two sounds. One is the sound, it's not the same little violin passage, but again, it's something recorded on one of these force sensors on the bridge. And then after that, you'll hear the effect of mixing it in with this body clonk noise. And now. Different, depends on how audio things don't always work on these Zoom things. I hope you more or less heard that. The first one perfectly recognizably as a violin and violin playing, but not a very nice violin. What my old supervisor Michael McIntyre always described as a kind of comb and paper quality to it. And that's essentially because it's always doing this sawtooth. It's got no character and it doesn't do anything very interesting when the player does vibrato. The second one had been mixed in with the clonk response of a particular violin and produced something which was maybe not a great violin sound, but recognizably perhaps more realistic. So what was going on here? Now, do you believe all that? Well, we have to ask yourself.
Jim, can you, I think people would like to hear those two examples again.
Okay. So here's the string. And here's with the body. If you're, lots of things I could say about that. Let's not do that. Right, so you ask yourself a sequence of questions. Do you think that different violins have a distinctive voice? Well, probably yes, you all do think that. Otherwise, what's the point? Here's a more difficult one. Do you think you could recognize the voice of a particular instrument from a single microphone recording? So without using both of your ears, without being able to move around, probably you think you could. It's not so easy. If you believe that, then all-ish the information about a particular violin is coded into that clonk noise as received by that microphone that you're going to do the recording with. So somehow those clonks capture everything that is worth paying all that money for in one instrument rather than another. In terms of sound, well, playability we'll come to in a bit. Now, Claudia will groan because she knows what I'm going to say next, but this is my moment to ride a hobby horse from years ago. How might we hear that? I'm going to give you a speculation. Now, you've heard the example I showed with the previous slide. I'm going to give a rather crude argument about what you might be hearing when you put that clonk noise together with a bowed transient. The sound demos on the previous slide were not the crude argument. That was the real thing. That should have been correct. Here's a crude version, which gives, I think, an interesting clue. And something I wrote in 1983 in the good old Catgut Society newsletter. You don't have to read this. Just marvel over the fact that it involved courier and typewriters and things back in those days. So here is a bowed string transient. And you will see this one again in a bit. So this is an actual bowed transient on it's a cello string, but that doesn't matter. Now, what do we see there? What we see if we take our glasses off is that the whole thing looks rather like this sawtooth, but some of the steps are bigger and some of them are smaller. And by the end, it's settled into a rather regular sawtooth, Helmholtz's motion. At the beginning, the sizes vary and the timing isn't quite regular. There are big ones and small ones. Maybe if you lay your ruler on this, some of them are a little late and a little early. Now, what happens? So we've got these sort of gentle ramps and occasional jumps. Well, as a first guess, it's the jumps that make the noise. The ramp doesn't make all that much noise. So when this ramp hits the bridge, it makes one of those noises, more or less. And then when this one arrives, it makes another one of those noises, and so on. Each one of these little steps arriving at the bridge makes a kind of copy of this clonk noise, delayed by various amounts and bigger and smaller. They might be, if it's a perfect start, they come regularly. They may, if it's a scratchy start, they may come rather irregularly. Now, that's rather similar to something else. Here you are listening to someone playing this violin here, and here's you elsewhere in the room. So the violinist does one note. The first thing that reaches your ears, of course, comes by the direct path. But not long behind that, you get reflections off the walls and the floor and the ceiling and so on. And then multiple reflections. And then depending how echoey the room is, they might carry on for ages. Now, there is a phenomenon in hearing called the precedence effect, which says that we're rather good at coping with this, presumably because we evolved in a context where hearing was important and where echoes were always there, trees in forests or whatever it may be. For whatever reason, we have got neural machinery that makes us rather good at processing this. Now, something you all know, but maybe you never thought about before, is that you would rather hear a violin recital in a medium-sized room than in the open air. Even quietly in the open air. Nobody likes playing outdoors very much. In the open air, more or less all you get is the direct sound. Maybe you get a ground reflection. Actually, you prefer to have some of these echoes. Now, if they go on too long, if it's recorded in a shower cubicle, so it's really echoey, then that gets muddying and confusing. But somehow we like early echoes. And this effect called the precedence effect says that your brain recognizes if a few echoes come early enough, within, I forget the numbers, 30, 40 milliseconds, some fairly short time, and they're sufficiently similar to the direct sound, your brain does something really clever. It recognizes that this is not a new sound, it's another version of the same one I just heard. And it kind of time shifts them. Somehow you end up hearing the sound more clearly rather than less clearly because of the effect of these echoes. So that's what we do. Now in rooms, it's definitely helped by the fact that they're coming from different directions. But even in a monaural sense, there is something of this effect. Now you think back to that violin transient that I was showing. what's it doing? The sound you hear consists of a clonk and then another clonk and a big one and a small one and a little irregular, and then settling into a regular pattern. And then we perceive it differently when it's regular. But the sound of a slightly scratchy transient, like a martelet bowing, has something in common with the sound of the early echoes in a room. So just maybe our brain processes these irregular copies of the clonk noise, and that just might mean that you're slightly better at discriminating one violin from another when you hear a rather scratchy, you know, a martelet, something like that, rather than a super smooth performance. The slightly irregular transient, as long as it's not so long that it's disturbing, might actually help you to get more of that information about the voice of that particular violin. It might not, it's a speculation. Right, now back to these two questions. Now, I'll move on to this second question, and this is going to be, what's the time? Oh yeah, okay. I'll talk about this till I run out of time. We've talked about the body affecting the sound. How does the body affect the player? These questions of playability. Now, this is a bit of a bottomless pit. I want to give you a little bit of a flavor of things we know about this, but that flavor is mainly going to make you go away with thinking this is horribly complicated, and you would not be wrong about that. Now, we can use, I'll show some examples, either measurements or computer models of bowing to investigate, at least in principle, we can investigate things relating to playability. What do people mean when they say, this one's harder to play, this one's easy to play? One thing they might mean relates to this series of questions. So the player does a certain thing with their bow. So you do a particular bow gesture. First question, does it produce Helmholtz motion at all? If not, you're a beginner and you know you need to keep on learning how to do it. If it does, how long was the transient? Remember that Goettler and Askenfeld stuff. How long was the transient? Now a trickier question. You try to do the same gesture again. So you do a similar gesture, but of course it's never exactly the same. If you do a similar bow gesture, do you necessarily get a similar transient from the string, or do you not? Is the system twitchy? You'll see why that's important. And then if we knew the answer to those questions, we could say, okay, how are those answers influenced by the properties of the instrument body, the properties of the string, the bow, the rosin, but keeping in our mind all the time that by far the biggest influence on these transients is coming from a player through those things we had before. So, back in the 1980s, in fact, starting in the 1970s, we had the first computer models of bowed strings, and we thought we knew how to do this. And by 1990, we'd been doing this kind of thing for a while. My mouse is giving up on me. Stop doing that. It won't move my mouse. Oh, never mind. So we had this idea that we wanted to use our computer models to do some kind of experiment in the computer to say, I do a lot of different bow gestures. Do they produce Helmholtz motion? How long is the transient? The things I just said. So I invented this family of gestures, thinking in terms of something like a string crossing transient, where you start not touching a string at all, you light on it gradually, and then your force grows to the steady value. Or something like a martelet transient, where you start with a rather high force and then you rather quickly slacken it off. So you might want to apply something a bit like these curves here, that the bow force varies in time, and it might start below your steady level and come up, or it might start above your steady level and come down. And we've already seen from Schelling's diagram that the actual steady level is important. So, and the significance of this family is that they're governed by two parameters, the final force and the initial offset. 2 is good because we can draw pictures in 2D. So I plot final bow force along here, initial offset, initial force as a ratio. So ratio of 1 means we simply switch the force on at a constant. Ratio less than 1 means it's like the red ones. Ratio bigger than 1 means it's like the blue ones. Each particular thing, like the pictures in the upper one, correspond to a dot in this diagram. Then we can get the computer to scan over them. And for those of you of a certain age, you should be reminded of the Mandelbrot set. Remember watching the Mandelbrot set? It's this sort of scanning a nonlinear system, drawing a nice pretty picture and seeing if you get interesting structure in it. And here is an example of something that we did. This is with Bob Schumacher, someone else who is late lamented. In its day, this was quite big computing. None of that really matters. This is a diagram of the thing I've just showed you. Each little colored pixel here is one simulated bow gesture in this plane. And they've been colored. If they're black, it means they never did produce Helmholtz motion. If they're colored, Helmholtz motion got there. The hotter they are, the quicker it was. So you get this idea that you could imagine doing this kind of thing, and you certainly get a picture with structure in it. I'm going to show you a bunch of these. With this caveat up here, I'm only showing you these for one reason. These are all wrong. We thought we knew the right model and we were wrong. But this picture, which I happen to have, does illustrate one really important thing, which is that this is simply 6 versions of that diagram from 6 different runs of the computer, varying a couple of parameters. And the first thing that jumps out at you is that they all look different. So this behavior, this is something to do with playability. See this one, if you had a real violin like this, you've got rather smooth terrain here. So you try to play a transient here perhaps, and then you try to do it again, and you get a similar transient, but not quite the same. But you get essentially the same answer because everything's varying smoothly. You do that on this one, and you might be on one of these red dots that produces Helmholtz motion really quickly. You slip off it just a little, and it doesn't produce Helmholtz motion at all. So the system can be really twitchy. You wouldn't like a violin like this. You probably wouldn't like a violin like any of these, in fact. But that's another story. And I'm not even going to tell you exactly what these are. But the fact that you get interesting behavior, you vary anything and the picture changes. This behavior is sensitive to everything. But then Knut Göttler came along. This is roughly when he came along, and he looked at this study we'd done and he said, but that's a load of nonsense. All of those are unphysical gestures, because any real gesture with a bow, either the force or the speed must start from 0. So if you're already on the string, if you've already on the string with a non-zero force, then you start the bow. Otherwise, it's already vibrating. On the other hand, if you do a string crossing, then if the speed is already there and then you land on the string, the force has to grow from 0. So it only really makes sense for real bowing if of the force or the speed. So he thought of a different family of gestures. He thought about doing transients where you start with the bow on the string always, you choose your force, and then you start the bow moving, and the other parameter you vary is the acceleration. How quickly do you get it going? So we've got force and acceleration, still 2 things because we want to plot a diagram. And that's what he did. So we'll call this the Göttler diagram. And he did a study that produced this rather confusing picture here. But just look at one of these there are multiple versions of roughly the same thing here. This bottom left-hand one here is Göttler's diagram. We've got bow acceleration along here and bow force up here. And what he showed by doing something none of the rest of us hadn't dared to do, which is to try to think his way through a transient and say, what do you have to do to get that perfect start? And he predicted that there's a wedge-shaped region in this diagram within which a perfect start is possible. And outside that, it is definitely not possible. And then what is varying on the vertical in these different panes of the picture is the bowing position. This parameter, always called beta, that's beta to you Americans, and it's the bow position as a fraction of the string length. So 1/12 is rather close to the bridge, 1/7 at the bottom is further from the bridge. So what you can see is that Gertler's wedge moves around. When you're bowing nearer to the bridge, the region is smaller, so it's more difficult, and you've got to be pressing harder for a given acceleration. You've got a smaller region to aim for. It's easier to play clean starts far from the bridge, more difficult near the bridge. No violinist is going to object, I think, to that general description. So, Knut produced this prediction based on a very simple model, and it's in some simulations on that model. We then did an experiment to see if there was any truth in it. So our ex-PhD student of mine built a bowing machine which could more or less do these things. Let me start by just showing you some of his measured results for Schelling's diagram. These are not transients, but remember the Schelling diagram, bow force, bow position. These are actual transients played on one string of a cello. It drove the technicians nuts because this machine went for hours on end, scanning this grid of noises. The computer has tried to classify what happens and squares our Helmholtz motion. So that I've marked one of the columns of this diagram, and this is actually the set of waveforms that go with those points. And what you can see is all the ones through the middle have got the Helmholtz sawtooth. The ones low down have got these multiple slipping. And the last few at the top are doing this irregular raucous thing. And yeah, it more or less agreed with the sort of thing Schelling was expecting. But we're interested in transients. So here are two transients from Paul's machine. Here his machine doing a perfect start. Here's actually the one I showed earlier when we were talking about the clonk noises and the room acoustics. This is a not quite perfect one, but it's not bad. And here is an experimental version of Gertler's diagram. This acceleration and normal force. Each one of these is an actual played transient. And the same thing, if they're black, it never did, within a finite time, do Helmholtz motion. If it's anything other than black, apart from green, greener ones his machine couldn't do. Any of the shades of gray meant it did produce Helmholtz motion. The brighter the color, the quicker it was. And that really bright white one in the middle there is one of these perfect starts. So that's a perfect start. So here's an experimental result. And this is interesting. This is a real bow, a real cello. You can see traces of Gertler's wedge, but it's quite speckly. So when you saw those colored pictures earlier, and I said this would be rather twitchy, and you may have thought, oh, real instruments can't possibly be like that. Actually, they are a bit like that. There is twitchiness going on here in this diagram. So can we predict these with our model? Well, the model that we thought was the right one back in 1990, and I said, don't believe these, it's all wrong. Here's what we get if we use the model we used to believe to predict this. And almost no aspect of that looks plausible. It's insofar as it's got non-black squares, they're not even in the right place. Here's a simulation using our current least bad guess for the modeling. It's another story to talk about what these models are. This is closer, but still not quite right. This one is too twitchy. This one is actually not twitchy enough. This is less twitchy than the real string. It's a bit too benign. And this is unfinished business. I've showed you these pictures to show that in principle, if only we had a model we believed, we could do interesting things in the computer to probe these questions of does the body behavior and so on influence playability? Could we classify instruments for ease of playing? And the answer is still probably yes, in theory we could, but we don't quite know. Now let me just wrap up with a summary of all of that. So transients means lots of things, lots of flavors of things. The body clonk noise is surprisingly important. If you want to convert what the string does into the sound in a single microphone recording, it's the only thing you need to know. So what I always tell people, you're comparing instruments like the ones fans sitting in front of. The first thing I would do faced with that table is that I would go along, hold the violin, damping all the strings, and just listen to these noises to think what sounds different. It's not very scientific, but if you don't hear a difference, two instruments that sound really similar, then I'm predicting you may find it difficult to tell them apart when they're played. If the clonks sound different, there's a good chance that in some kind of blind listening test, you might actually be able to tell the violins apart. That's a prediction. It may not be true. The transients the player produces by bowing a string are far more complicated. They're mainly determined by the player, and that's why you have to do all those years of practice so that you nearly all the time produce acceptable transients, and you can pick up any violin, and with not very much lead time, you probably still produce acceptable transients. Something that's really different, like a solid body electric violin, you may have to tune in a little bit. It will feel different under the bow. But mostly players have just learned how to do this thing, and Goettler's diagram gives a clue about what it is they've learned to do. Now, Claudia's thing. Do you remember those sound examples I played you of the string noise and then the incorporating the body clonk noise? This is something we called virtual violins, and Claudia did a project on that. There's still mileage in that method. It's this hybrid approach of using real recorded string motion from a real violinist, but physical measurements on violin bodies and turning that into a version of the sound and then doing listening tests based on those. We did some things with that. There's more that could be done with that. It's quite a powerful method. What about ease of playing? Does the vibration of the body influence things the players would say to do with playability? Well, certainly for steady bowing, there are strong effects, and the classic example is the wolf note. And the things that are definitely there, and I've given talks about this before, some of you may have heard, relate more to Schelling's diagram, to steady bowing. That minimum bow force line in Schelling's diagram is sensitive, very sensitive to the body behavior in a rather predictable way. So different violins, other things being equal, may have different minimum bow forces, which means the range of allowed forces may be wider or narrower. A player can certainly be aware of that. The wolf note is essentially a note on an instrument where that range closes down to something really narrow. And then if you're just outside it, you may get the funny warbling effect. So certainly for steady bowing, there are body influences on playability. Does it influence transients? Oh, I'm sure it does, because I showed you these pictures showing that you take anything you vary does influence the response to transient bowing. But is it going to be a characteristic of the violin? No, it isn't. It's going to vary from note to note, I'm quite sure, as the wolf does, of course. So there may be individual hard to play notes, and that may be about steady bowing, but that there may be transient related effects perhaps there, but rather hard to get a grip on. So in principle, we can use computer models to explore those. It's a great idea in principle, but despite many years of effort, as it says, and this, we had these first models in the mid-70s. It's an awfully long time ago, and we're still struggling. We don't have a sufficiently accurate model that I really trust it. We get some qualitative guidance from these models, but I could not say that the model will get it right enough that I could take a particular violin and predict reliably the playability of that. That's unfinished business and something we may want to come back to. And at that, I wrap up. Thank you. Oh, I didn't overrun too much.
Thank you, Jim. So just a reminder, if you have questions, please use the raise hands function. So are there any questions? Jesus.
Not hearing you. Still not hearing you.
You hear me now?
Yes,
Okay.
yes, we hear you.
Okay, go ahead.
Thank you. Nice to see you again, Jim. I was thinking this question since your conference was announced, but I think that you responded in your last words. Even so, I am trying to obtain sound from a finite element model, injecting a synthesis of the bow force. My first approach was using your force in the force that you are showing in your CAS journal paper and the Caruso paper, which have a very nice Helmholtz motion, but it sounds like an Atari sound. It is not real at all. Even if we cannot to simulate now a good bow force, I think at least we can improve it. So if we have the initial transient, like a line, and then the Helmholtz motion, how can improve this very simple model to be used in my finite element model? Thank you.
I wish I knew the answer to that. It's synthesizing bowed string motion. It's one thing to synthesize the motion for a known bow gesture. It's quite another thing to synthesize something that sounds like realistic violin playing when you listen to it. We had an experience with that. Claudia will be wryly smiling at this one. We have an idea that vibrato, one of the things that the body response relates to is how sensitive it is to vibrato. And I'm sure there is an effect like that. And we tried to do a proper psychoacoustical experiment to demonstrate that effect. And we failed. We managed to write a paper saying we tried this and it didn't work. We tried that and it also didn't work. And we amazingly got that through the journal. But that was the short summary. And that roughly speaking, what happened was that we've made, because if you want to vary the vibrato amplitude or frequency or something, you really need to use synthesized force rather than a measured bow force. And so we would have people listening to things saying, do you prefer this or that? Does this sound more rich? And the violinists would say, I don't like all of them. They all sound horrible. None of them sounds remotely realistic. And we tried all kinds of little tricks of introducing a bit of irregularity and a bit of this and a bit of that. And it didn't make any difference. We did not crack the problem of making synthetic things that allowed us to control one variable without having all manner of other complicating factors. So you don't really want transients for this because people hear other things like that piano demo at the beginning. So I think what you've raised is a really hard problem. Now, I'm not in the sort of music technology world. The people who do musical synthesis for real, now with Gary Scavone's here, he may be more up to date with some of these things. I dare say the people who do modeling of this sort of physical modeling synthesis have probably got better at doing this. I bet they still can't do it, but they're better than they were. But as a minimum, I think that a computer model of a bowed string probably has to be played by a person controlling the variables rather than predetermining them in a program. And the person may have to practice just as long to learn to play your program as they took to learn to play the violin in the first place, and nobody can be bothered to do that. So far, I think that there's been a real difficulty in having synthesized things that don't instantly strike people as unrealistic, and to the extent that they can't make musical judgments because it doesn't reach the starting gate of sounding like a realistic violin. So that's a non-answer to your question. I think that's it's a tough one. I've sympathized with you, and But if you crack it, do let me know, and we'll steal it.
Then even before that, using any simulation of the bow force in a body in a model of the body, then we need to obtain a good sound from the bow force, even before that we are using it, right?
I think that's right. You need a good bow force. Yes, modeling the body is straightforward. I mean, that's when I said plucked instruments are easier. We can do a pretty good job of a cold synthesis of a guitar or a banjo, as I've been involved in recently. And they're quite recognizable. They're not great, but they're okay. They get around this problem of people saying they all sound horrible. I'm not going to listen to those. I can make a guitar synthesis, say just from cold, from a physical model that is perfectly recognizable as a guitar, and you make parametric changes and people recognize it. You know, you're playing a bit closer to the bridge, or you've got a different type of strings. So provided everything is linear, we can do it. If the string and body motion is linear, then the models are pretty good. It's the non-linear bowed string motion which makes things difficult. But that's where this hybrid method comes in. If you record actual bow force from a real performance, then you can play that through, whether you use measurements of violin bodies or models of violin bodies, you can do that, and they'll sound all right, and you can vary parameters. Not easy to get a really good model, but that's a different matter. But it's the really tough part is the nonlinear bit and the bowed string models, and controlling that in a way that sounds interestingly realistic. Now, I suspect that all the people who do, you know, natural language understanding and that kind of thing, probably now, if people tried hard enough, you know, the world chess champion and Go champion have both been beaten by computers. If people were prepared to put enough effort in, we probably could make something that generates bow gestures that are not too different from a real violinist. But it might be a big computing project, not a violin maker's workshop kind of project, or a superannuated retired engineers kind of project.
Okay,
all right. Thank you. Next is John Gilbert.
Hello, thank you.
Hi.
Inspirational. I put my question in the chat, but I'll just go ahead and read it just to so everyone else gets it. When you did the Boeing robot experiment, you had these specular places where the transients, the results never went to a good Helmholtz.
Yep.
Were those repeatable? And part of that is in between each bow event, what was the reset?
Okay, those are good questions. The answer is no, they're not repeatable. It's the specularly pattern is statistically repeatable, but the individual spots, even with a computer-controlled system and resetting and everything at rest, there was enough variability. The system is genuinely twitchy. I mean, the 1990s, for those old enough, it was the glory days of chaos theory and the butterfly effect and all that sort of thing. And the bowed string, the real bowed string to some extent, and certainly the computer models have something of that in them. There is super sensitivity to initial conditions. I'm fairly sure that's genuine. Exactly why, if I knew exactly why, I'd be doing the next version of the model. But the hard part is understanding rosin fundamentally. It's getting the right physical law for the frictional interaction. We can model the bow, the string, all the linear things. It's right there in the contact region where the friction happens. That's where the nonlinearity is. And nobody in any context of friction excited vibration has a physically based model which just works from cold. For any particular thing, you can fudge something up that matches a particular measurement reasonably well, but that's cheating.
Thank you.
All right, thank you, John. Next is Gary Scavone.
Great,
Hey, Gary.
thank you. And thanks for a great talk, Jim, as usual. Just a quick comment about the control. There have been people that have looked at that. And if you do record the controls at a high rate and then synthesize at a fairly high bow control rate, you do get much better results. And that's promising, but it's hard work. So, but I have kind of just a less serious question. I'm just wondering why you always refer to the sounds of the violin that you get as noise.
Do I always do that? Okay.
I thought some people might be a little bothered by that, but I just thought maybe it was some decision you made to stay away from subjectivity or something.
Oh, well, yeah, I don't think I intended anything really pointed by it. More noise, less noise. Yeah, no, it's yeah. No, I don't think there's a deep answer to that one. Good to see you.
All right. Next is Joseph Najivari.
You need to unmute.
Unmute.
Okay, we can hear you now.
My own?
Yes.
Yes. Okay. I would like to ask something which you have not discussed, but I think it belongs very much to the problem of transients. You are probably familiar with the work of two Czechoslovak researchers, Stepanek and Otsenasek, who were probably among the first to study the actual power spectra of transients on long played notes with different bow strokes. And I believe even before them, Askenfeld reported at a meeting that the spectrum of the transients reveals major peaks of the frequency response curve. So we are not really speaking about a general noise. When we talk about noise, that's a pretty broad spectrum, something rather flat, but this is something very distinct. And
yeah, well, it's this clunk noise.
Yes.
It is the thing I was trying to talk about. That is a linear combination of the body resonances. And you may hear that in a robust starting transient through this precedence effect mechanism.
Now, if I may finish actually my question, you know, I looked at several violins, recorded long time averages of martelli, bow strokes, and so on. And I see huge differences between violins. All of them had big peaks at the B1 plus, B1 minus, and the air resonance. Some of them have very strong peaks at high frequency, around 5,000 and 6,000. And those violins, when you start and play Baroque music, begin the note with a very clear click. And I wonder if you think that this is a useful property of violins, that you can start with a high frequency clicking transient, or not necessarily so. So what do you think about the distribution of power in average transient spectra?
Well, that's an interesting question. We've thought about those kind of questions more in terms of steady bowing, but these things happening at a few kilohertz take us into the realm of the bridge hill, or both the two bridge hills, which have been a matter of a lot of work in recent years. And violins certainly too differ in the height of those hills and in the frequency placement of them. And certainly you hear the effect. I've never really thought about that in the context of transients, but you're quite right that it's there in the clunk noise, and so it's there. And because they're high frequencies, your description of a sort of click-like start sounds very, very plausible. It's an interesting thought. It could be investigated neatly by this hybrid violin method, I think. You could take different body responses, real or, you in the computer, you can artificially modify things and see what you have to do before people notice this clicky start. But that's an interesting suggestion. Thank you for that.
Okay, thank you, Joseph. And one final question from Christopher Dungy.
Can you hear me?
I can.
Yes.
Thank you, Jim, for your presentation and being able to share with so many different people, different locations around the world. So is the end goal for transients being part of the string instrument, is the end goal to produce a perfect transient? Is the first question. The second question, if that's true, then I would think trying to find the right bow matching the right instrument would enable you to produce that perfect transient. Is that how I'm understanding this?
Let me, on your first question, end goal, do you mean end goal for me as a scientist or end goal for a player?
End goal for the player.
For the end goal for the player. Now, I'm the wrong person to, this won't stop me speculating, but you wouldn't want to hear me play any of these instruments. I would say that an important goal for any player is to be capable of producing sufficiently perfect transients when they want to, and then to have the control to, it's not that they do it all the time, but when you don't do it, you want to not do it deliberately for musical effect, rather than because you made a mistake. So, learning the fineness of control so that when you want clean, clear scale, you can do perfect popping notes one after another. And when you want to do something else, you know what kind of bow gesture that would require. So, I mean, so the Gertler-Askenfeld study showing that players, without knowing what the experiment was for, when just asked to play regular repertoire items, the most common thing they did was to produce perfect starts. Now that doesn't happen by mistake. They have learned to do this. And as I say, Gertler got involved in this as a bass player. When you're from the cello, bass is, of course, even more of the same problem, that really 5 cycles and the note's over, So he was trying to learn things that he could use with his pupils. End goal is probably the wrong phrase, I think, but it's a direction of travel. Right? You never end, because you get older and you get worse again. But can you push your pupils such that they get better control over these things? He had all kinds of interesting tricks that he used to do. That's another story. Now I've forgotten what your second question was.
Well, the other part of the question was if that's what
yes.
the player is, in other words, give a player 12 instruments but one bow, and then they throw out 11 instruments because they didn't do what they were supposed to do. Could that have been an issue with, it was the wrong bow matching that particular violin that didn't produce the perfect transient?
It's a good question, and I don't think anyone really knows the answer. There's been a bit of work on characterizing bows. There's been a bit of work on including bow dynamics in these computer models of the bowing process. All of those things indicate that the bow has an effect, but it always seems to come out as a more subtle effect than players will tell you it really has, if you see what I mean. So I think we don't really understand how it is that players think bows vary so much, and I don't doubt it. It's the whole of this subject, musical acoustics, is like that. That in any other kind of vibration problem, I would be consulted, and expect to be the expert while the end user tells me their problem. With these things, instrument makers and players already know how to do it. I'm kind of chasing along behind, trying to understand what they do. So I don't doubt that people are describing something which is real and matters to them. We haven't yet managed to pin it down into anything really clear. The only thing we have pinned down is to do with bows is a rather different thing. I know I can see Murray Campbell down there. There's for some reason on viols, as opposed to the violin family, Murray found a phenomenon that we've kind of almost pinned down, where there's a measurable and audible effect coming directly from not bowing straight, you know, not bowing perpendicular to the string. Now, you're always told you should do it, and you say, why? And in viols, we can see, and that does seem to be to do with a bow hair resonance, somehow interacting with how the string vibrates. There's unfinished business there, but that's the only example I've been involved in where we've actually found something we can measure, which is definitely connected to some aspect of bowing. Other things, I just don't know. There's a wide open field here, but it's a wide open field, not because people haven't thought about it, but because they haven't managed to do anything. So I suspect these are hard questions, but nonetheless interesting for that. These people who instrument things while instruments are played and then work out what players are doing, they may know more about this. And one thing, I had a bow somewhere. One thing that is rather easy to do, that there's a convenient place just behind the heel at the tip of a bow where you can stick a little accelerometer, which doesn't interfere too much as long as you can get the wire out of the way. So you can fairly easily record vibration in the bow while someone is playing in a fairly non-invasive way. And you certainly see stuff going on there, but does it matter for the bowed string? No one has a clear answer to that. I mean, it's a good question. It's been suggested before, and I've not found a good way to get a handle on it. I suppose that's why, can I see an experiment to do or a model to build? Not entirely. You know, you can build it, you can build these effects into models, but the models are enormously complicated by the time you've got all these things in. And then you've got a model with 200 parameters. And so what do you do with the model? What do you vary? What are you looking for? These bowing simulations show that the behavior is sensitive to every single thing you vary. And that's not a very helpful conclusion. You know, we can't see the wood for the trees at the moment. These problems are messy. You've raised another aspect of messiness. I'm absolutely sure that it's relevant, but exactly how relevant is a good question. I mean, one of the things that must happen, if transients are affected by the bow, it must make a big difference whether you're bowing near the heel or in the middle or near the tip, because near the heel, the dynamics of the bow and the bow hair hardly do anything at all. It's all rather rigid. So you shouldn't notice much difference between bows if you just did bowing. That would be my guess. Once you're out in the middle or up near the tip, then the fact that the stick may be vibrating and the hair might be vibrating, there's scope for that interacting with things. So I guess that's the first experiment. One might think maybe this is an Oberlin thing. You know, you assemble some things and some bows, find bows that people are, you say, I guess you want 1 cello and 10 bows. Find things where people do think they're different. Then I would ask the question, if you only allow yourself to bow near the heel, can you still feel or hear that difference? And if you can, then it's something else. Maybe it's your brand of rosin rather than your bow stick as such, but you know, so you can begin to see how you might creep up on this problem, but at the moment we can't see the wood for the trees.
Okay, we have one last question from Claudia because she wasn't able to raise her hands.
Yes, thanks, Jim. You know, you mentioned the amazing opportunity by, you know, convoluting the bow, the string, and the body behavior. and yeah, using this to investigate some of playability or other aspects. But that means that we assume that the coupling is, there is basically the string vibration is the same for every violin and is not influenced by how the body vibrates, and that's just a first assumption. So
absolutely. Well, it's cleaving the problem to answer one kind of question where at least we can see how to do it. Now, as soon as you're back into the whole playability thing. Once you say, does the body influence either what the bow does or what the player has to do in order to make a nice noise, you're back into this sort of jungle of playability questions, which I've been fascinated by for decades. And we've tried
the transients, no? Don't you think don't you think that influences the transients?
It will do. It'll influence everything. That's I mean, that's what those computer studies show. You vary any parameter in your model and it does influence the transients. I suppose the question you have to ask, which is more difficult with a computer model, is it's not so much if you do exactly the same gesture, do they behave differently? It's if you hand this bow or that bow to a player, they may adjust what they do. Can they, by adjusting what they do, get an equally good effect? Or do some bows make it difficult for them to do the adjusting? There's a psychophysics issue of the player being inside a feedback loop, which you're only too familiar with. So there are good questions in here, but they are hard ones to start. And so on the principle of doing the easy things first, this is one I'm happy to leave on the back burner for the moment. That's not the same as forgetting it, but until someone has a good idea. But this trying just bowing near the heel is a good, next time you're handling, Chris, now, some two bows that you think are really different on a given instrument, one of them really suits it, just ask yourself, can you still feel that difference if you stay near the heel? Because that will be a really interesting data point and would give us a start on what to do.